Hey again, organic chemistry. So this is part 3 of our video notes on mass spectrometry. We're going to continue on. In the end of the last video, I quickly went over these two rules that we'll see in mass spectrometry. One of them is if I have a molecular weight that's odd or an M plus ion, that I typically will have nitrogen. We call it the nitrogen rule. This really happens if I have an odd number of nitrogens. And most times, especially in high school organic chemistry, I'll have one nitrogen in the compound to give you an odd molecular formula. Nothing else is going to give you an odd molecular formula. And then our second rule or thing to consider is the presence of bromine and chlorine indicate is indicated by suspiciously large M plus 2 peaks. An M plus 2 peak, and I kind of drew a picture here, is if I have a mass spectra, and I showed you a mass spectra a couple of times in these notes, but again, mass spectra, we haven't talked about what any of these peaks mean, but these peaks are different mass, and I have my M plus molecular ion peak, which is the molar mass or the molecular weight. If I have an M plus peak and then eventually an M plus 2 peak, that means I must have bromine and chlorine present. Okay? Just going to skip this little thing here about the example. This is just an example of calculating a molecular weight. So anyways, the M plus contains the bromine isotope. If its intensity is 100%, the M plus 2 due to bromine 81 will be 98%. What this means is this is bromine with a mass of 79 and bromine with a mass of 81. That's what 81 bromine means. Isotopes wise, if you see it, if I have a sample of bromine, if I had like 100 particles, 100% of the particles could be 79. If I have even more particles between the two of them, if I have like 200 particles or 198 particles, 100 of them would be bromine and 98 of them would be bromine 81 and 100 of them would be bromine 79. I know that sounds a little bit confusing, but isotopes, again, are elements of the same kind but have different masses. Now, because of these percentages, if I were to have an M and M plus 2 peak for bromine, we'll see this later. If I have the M plus peak, the M plus 2 peak is going to be about the same height, if not a little bit shorter. For chlorine, we're going to see that the percent abundance is a little bit different. If I had like 133 samples, 100 of chlorine, 100 of them will be a mass of 35, and 33 of them are going to be a mass of 37. If I'm going to see chlorine in my mass spectra, I'll have a peak that is M plus up here, and then about a third the size is M plus 2. This means I have chlorine. If I have an M plus and an M plus 2 peak, that means I have bromine. Right? So just keep that in mind, and we're going to write that down here. This is just, again, introductory. It might sound a little confusing. We're going to go back into it again. But again, the most common for us in high school is chlorine, like I said up here. Chlorine's M plus to M plus 2 ratio is going to be 3 to 1. And so again, what I drew up here, what it's going to look like is I'm going to have my M plus peak, and my M plus 2 peak is going to be about a third of the size. And then bromine M to M plus 2 peak is going to be about 1 to 1 in height. So if I have M plus, my M plus 2 peak is going to be about the same size. This is very important. Very important. Okay? So here are two examples of mass spectra. Again, we haven't really talked too much about what goes on in the mass spectra. But if I look over here, I have an M plus and an M plus 2 peak. M plus 2 is a third as large as the M plus peak. So if you put kind of like a box around here, this means I have chlorine in my compound. Again, if you zoom in, my M plus peak is a mass of 78, and that goes up a bit. And then my M plus 2 is a mass of 80, and it's about a third the height. This means I have chlorine, means I have Cl in my structure. So you'll see questions in the future, just put a star here. You'll see questions in the future that'll say what element is present. And if you see the M and M plus 2 peak, that means I either have bromine and chlorine. And if it's a third the height, if the M plus 2 peak is a third the height, that means I have chlorine. For bromine, look over here. Like I said over here, it's a 1-to-1 ratio. For bromine, right here, the peak is 1-to-1. M plus and M plus 2 peak. The M plus peak is 122. M plus 2 is 124. M plus 2 means 2 plus my molecular ion. And they're about the same height. Same height. So if you get a multiple choice question or a short answer question that says what element must be present or what element is missing from the formula, and you see an M plus and M plus 2 peak, again, it could be either bromine or chlorine. If the heights are the same, it's going to be bromine. If the heights are about 1/3 each other, it's going to be chlorine. Okay? All right. So we're about to move on to a bigger part of mass spectra, which is what these other peaks mean. So now on the next page, we have typical fragmentation in mass spectroscopy. So mass spectroscopy is also used to study large organic molecules. Yep, that's what we do. When a sample of a pure compound is analyzed in the instrument, some of the molecules get ionized into molecular ions. M over Z, M plus, okay? While some are fragmented and ionized. The fragmentation occurs in predictable patterns, allowing scientists to propose chemical structures for unknown substances. Consider the mass spectrum of pentane. All right, so here is the bread and butter of how to read mass spectra. We're going to see a bunch of different lines which correspond to different fragments, okay? So we have masses here. All right, this is a mass peak of about 72, peak of 57, peak of 43, peak of about 29, peak of about 15, okay? This is the M to Z ratio. All right, so keep in mind these masses and the differences between these masses. So let's talk about pentane for a moment, and we know how to draw pentane. Pentane looks like this. 1, 2, 3, 4, 5. It's C5H12, and it has a molecular weight of 72. So this is technically right here. This is the M plus peak. That's the whole pentane. E has the entire pentane, but it must be positively charged. If you remember a couple of pages back, when we throw our molecule into the mass spectrum or mass spectrometer, it's bombarded with high energy electrons, causing electrons to be ejected, so they're positively charged. So once we throw pentane into the mass spectrometer, electrons pop off, and so it becomes positively charged, and I'm probably going to have my entire pentane at E. So if I look at all these different fragments here, it says match the molecular ion and fragment ions below to each of the lettered peak clusters in the mass spectrum. This top one is going to be E. This has a mass of 72. Okay? And so this peak right now is this. CH3, CH2, 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 CH3, but with a positive charge. And this is my M plus peak. Then I have peak D. If I notice the difference in the mass between peak E and D, and this is what you have to do when you start doing mass spectroscopy. If I notice the mass difference between E and D, going from 72 to 57, if I subtract that, that's 15. This is a loss of 15. I'm going to say mass of 15. Something must have come off this molecular ion that has a mass of 15. Well, what in this structure will give me a mass of 15? I mentioned this earlier, but if I ever have a loss of 15, I must have lost loss of CH3. A mass loss of 15 means I lost a CH3. That means we could probably cut off this ending here. I must have, like, I mean, it doesn't matter which one, but I must have lost a CH3, which means I'd be left with the rest of these carbons at peak D, which would have a mass of 57. 1, 2, 3, 4 is 48. 49, 50, 51, 52, 53, 54, 55, 56, 57. So these 4 carbons right here must have a mass of 57. So peak D must be the 4 carbons. And that has a mass of 57. It lost a CH3. And then if I go from 57 to my next big peak, I'm looking at like the highest peaks. So I'll put like a point on them so you know where A, B, C, D, and E lie. My biggest peak here at C has a mass of 43. That is a loss of 14. What in the rest of this structure would help me lose a mass of 14? Well, that's a loss of a CH2. Now, I must have lost another fragment, which would be my CH2. This is how mass spectrometry works. I keep on breaking apart into pieces, and the mass spectrometer is going to read that. So now I'm going to be left with these 3 carbons, and this is going to be a mass of 43. 3 carbons is 36, 37, 38, 39, 40, 41, 42, 43. This M43 peak is going to be CH3, CH2, CH2 plus. That is what is at peak C. And this has a mass of 43. I lost CH3 and a CH2. Continuing on, going from 43 to 29, you've guessed it, that is another loss of 14, which is another loss of CH2. If I lose another CH2 at this mass of 29, I must have CH3, CH2 plus at peak B. This is peak B. That has a mass of 29. And then you've guessed it, if I have a mass of 15, I must have CH3 plus. This is a mass of 15, and that is peak A. Okay? Each of these peaks corresponds to these fragments. I didn't mention it over here, but 57, a mass of 57 is going to be this fragment, CH3, CH2, 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 with a positive charge. 4 carbons, and the 3, 4, 5, 6, 7, 8, 9 hydrogens. Okay? This is how mass spectrometry works. The whole molecule starts breaking apart, and the reader reads specific fragments that have specific masses. You're going to have to be able to interpret those specific masses. Some important masses to consider, and you're going to have to know for mass spectrometry, mass and fragment, and you're going to see this on the next page. If I have a mass of 15, that is definitely CH3. If I have a mass of 29, that's going to be CH2CH3. Don't forget that CH3 is methyl and CH2CH3 is ethyl. This is going to come up a lot in the work that we're doing. And then finally it says peak A has a small peak at 14. What may have fallen off of the CH3 ion to form this peak? Well, we said the mass of 15 is CH3 plus. What would give me a mass of 14 then? Well, the only way to go from 15 to 14 is by losing a hydrogen. So I must have lost an H plus, or lost H. So I'm going to say this is plus, and there we go. I must have lost an H. That's just like to keep in mind of masses, okay? So I'm going to end this video here. We are going to pick up with understanding and doing more work on fragments when I return. So for class, you are going to be copying these notes. Again, to recap in the very beginning, I'm going to go back to the beginning. I briefly talked about what mass spectrometry is and defined it. And then I kind of gave you a peek of what mass spectrometry is going to look like and how the different masses represent things and how we have to calculate molecular weight. I then talked about how a mass spectrometer works. And you're going to have to know about these 4 different parts or stages of the process in mass spectrometry and know that mass spectra only read positive ions. We then did a sample quiz question in which if I give you a mass spectra, you have to choose the molecular formula that matches the mass spectra if it matches the molecular weight. And then I quickly showed you how to calculate molecular weight as a little bit of a recall, just using the periodic table and the masses of the elements rounded to the nearest whole number. Adding up all the different elements in the compound gives you the molecular weight. And then I introduced us to the nitrogen rule and the n+2 rule. You'll have an odd molecular weight if you have at least 1 nitrogen or odd number of nitrogens in the compound. If I have bromine or chlorine, for high school organic chemistry, we're only going to care about bromine and chlorine. If I have bromine and chlorine, we're going to have an M+ or a molecular ion peak and then an M+2 peak. If the M+2 peak is 1/3 the height, it's chlorine. If the M+2 peak is the same height, it's bromine. And then we ended with talking about how we interpret all the different peaks in a mass spectra, and each of the peaks correspond to specific fragments. What you will eventually have and get is you're going to see what the masses correspond to, and I gave you some very important ones. 15 and 29 are big in organic chemistry. But what you'll see is you'll have a list of masses and what fragments they correspond to, and that's going to help you build and create your structures. In class, we're going to be doing some practice. So on the next page, on page 7, you'll be doing some practice with fragments and recognizing what compounds or what is in my formula, and we'll do that in class together. We're also going to do in class together common fragments and their masses. So we'll talk about this the next I see you.